In our last lecture, we have discussed the fundamental ideas behind Gaussian elimination. We know Gaussian elimination solves system of linear equation of the form summation j equal to 1 to n aij x j equal to bi for I equal to 1 to n. We also know that Gaussian elimination consists of two steps. First one is forward elimination and second one is back substitution. So far, we have seen how to use Gaussian elimination for two equations, two unknown systems, and three equations, three unknown systems. Then there were exercise. You must have done the exercise for four equations, four unknown systems. But in reality, the number of equations and the unknowns will be many more. It could be hundreds or thousands and maybe even millions. So here we will now discuss how to generalize the idea of Gaussian elimination to an arbitrary n equation, n unknown type system, and at the end we will write a pseudocode for Gaussian elimination. Let us take once again this linear system a11 x1 plus a12 x2 up to a1 and xn equals b1, a21 x21 plus a22 x2 all the way up to b2, and an1 x1 an2 x2 up to bn, this sort of a system. In Gaussian elimination, what we do, we pick a pivot. We start with the pivot a11 and then our goal is to use this pivot such that a21 becomes 0, a31 becomes 0, all the way up to an1 becomes 0. Once we do the operation, we also change all other coefficients that are there in equation 2 to n. Equation 1 of course remain unchanged. Then we go to the pivot a22. Of course a22 is now changed after the first operation, and we use a22 to bring all zeros below a22. In this operation, we do not do any further change in equation 2. If we continue in this way, we will have this system of equation where the equation 1 has no change. However, in equation 2, we see the first term is now out. It starts from a2 to x2, but this is not the old a22. It has changed, so we are putting a prime here. Similarly, all other coefficients in equation 2 has changed to prime. On the right hand side, b2 has also changed to b prime. Then if we go to equation 3, we will see that first two terms are now out. It will start from a33x3 and all the way up to equation n, where we will see we have only one term, ann xn, and we have right hand side bn. Of course, the ann is now primed and bnn is also primed. It has changed many times, and this is the final form of ann and bn. Nevertheless, the last equation we see that only one unknown, so it can be solved for xn, and then we can go back in back substitution and we can serially solve xn minus 1, n minus 2 all the way up to x1 here. However, before we go into back substitution, first let us try to generalize the forward elimination for an n equation, n unknown type system. So let us take forward elimination of column 1. By column 1, we mean that whatever falls from a11 and below that. So in column 1, our operation is that in equation 2, a new equation 2 we write, which will be old equation 2 minus equation 1 multiplied by a21 divided by a11. a11 is my pivot when I am doing the operation in column 1. a11 is the pivot. a21 corresponds to the coefficient of x1, equation 2. So this is equation 2 coefficient of x1. That gives me a21. When I do this operation, in my new equation 2, there will be no a21, a21 will be 0. We do a same operation in equation 3. In this case, new equation 3 is old equation 3 minus equation 1 multiplied by a31, that is equation 3 coefficient of x1 divided by a11. Now we can carry on doing this all the way up to equation n. If I do so, then my first column below a11, all the coefficients will be zeros. So we don't recalculate those coefficients, we don't write those coefficients, we just know that they will be 0. But we have to see what happens to the other coefficients, because we are doing something to the equation. So all the coefficients in the equations will change, and also the right hand side means this b2 to bn, they will also change. So all those changes we have to store. A21 to n1 are 0, we don't care about that, but who are not 0, their changes we have to store. So we generalize this operation first as equation I is equal to old equation I minus equation 1 multiplied by ai1, that is equation I coefficient of 1 divided by a11, which is my pivot. And this operation I will do from I equal to 2 to n, that means equation 2 to n, not in equation 1. Equation 1 remain unchanged. I am taking a11 as my pivot and I am operating for equation 2 to n. When I do so, my bi's will change and my new bi will be old bi minus b1 multiplied by the same multiplication factor that we have used in equation I, that is ai1 divided by a11. Similarly, all the coefficients in equation I will now change. In equation I1, ai1 has become 0, but what happens to others? We have to register that. So aij's will change for j equal to 2 to n. For j equal to 1, that is ai1, and that has new ai1 is 0. We don't talk about it anymore. But we see what happens to aij's for j equal to 2 to n. It becomes the old aij minus of a1j, the corresponding term in equation 1, because we are taking this equation 1 multiplied by a factor. So aij is changed by old aij minus corresponding jth term in equation 1 multiplied by the same factor ai1 divided by a11. Now we see another example, that let's say in column 2. So in column 2, our pivot will be a22, and in a22, having my pivot, we will operate first over equation 3, which will be old equation 3 minus equation 2 multiplied by a32 by a22. A32, once again, it corresponds to equation 3 coefficient of x2. Similarly, if I operate over equation 4, it will be old equation 4 minus equation 2 multiplied by a42 divided by a22. a42 is equation 4 coefficient of x2. Once I do this operation, of course the new a32, new a42 will be zeros, which means that all the coefficients below a22 will be 0 now. But we have to generalize for equation I, and in this case I goes from 3 to n, not 2 to n. Equation 3 will change, nothing will happen to equation 2 here. we are talking about column 2, our pivot is A22, and when we are operating with the pivot A22, we'll change the equation 3 to n. Equation I will be old equation I minus equation 2 multiplied by a factor. That factor is AI2 divided by A22. AI2 is equation I, coefficient of x2. My BI will change at BI minus B2 multiplied by the same factor AI2 by A22, and AIJ will change at AIJ corresponding element in equation 2, that means A2J multiplied by same factor A22 AI2, and now it will go from 3 to n, not 2 to n. So when my pivot is A11, I am operating between 2 to n. When my pivot is A22, I am operating between 3 to n. If my pivot is k, I will operate between k plus 1 to n. Now, let us summarize what we have just learned. We started with an usual system of linear equation, n unknown, and we have seen that the first step that we have taken, that goes between I2 to n. Here my pivot was A11, and in this I2 to n, what it did is that it changed all the BI's, which is old BI minus B1, into this factor AI1 by A11, and for I2 to n, J2 to n, it will change all the AIJs, which will be old AIJ minus A1J minus multiplied by AI1 divided by A11. Similarly, when I go for I equal to 3 to n, at that point my pivot is A22, my multiplication factor is AI2 by A22, B is changed, BI is old BI minus B2 multiplied by AI2 divided by A22. For j equal to 3 to n, all AIJs will change with AIJ corresponding element in equation 2, that is A2j multiplied by same factor AI2 divided by A22. Now we will go for one more step of abstraction. We identify the pivot element as our diagonal elements A11, A22 all the way up to An-1, n-1. Of course, this A22, when we will use A22 as a pivot, it will change once. Similarly, all other pivots other than A11, they are not in their original state when we will start using them as pivot. All of them will be changed. So in a sense that we say that our pivots are the diagonal elements which are given by AKK. K goes from 1 to n-1. We are not taking all the way up to n because ANN we are not using to make anything 0. That is the last diagonal element. So in a sense that is not a pivot at all. So let us now generalize. Here the k corresponds to pivot element. If k equal to 1, my pivot element is A11. If k equal to 2, my pivot element is A22. So for in general k, my pivot element is AKK. And as I know that when my pivot is A11, I am changing I equal to 2 to n. When my pivot element is A22, I am changing I equal to 3 to n. So when my pivot is k, I am changing I equal to k plus 1 to n. And in this k plus 1 to n, I am certainly changing BI's, which is old BI, minus B corresponding to the equation from which I am taking the pivot element. So minus BK multiplied by a factor AIK divided by AKK. AIK is the ith equation and this is the coefficient of xk. Now I have changed B. I have to look at the other coefficients of the ith equation Aij, and here I'll go from j equal to k plus 1 to n. As much as I is going k plus 1 to n, j will also go k plus 1 to n. This will be old ij minus akj. This is the pivot row corresponding element, that is akj, multiplied by the same factor aik by akk. This is sort of a pseudocode. This is not complete yet, but this is the first step in writing a pseudocode. And what I suggest you that you focus on writing this correctly. You forget about writing the program. In your homework, you will be asked to write a program, but you forget about writing the program. You focus on the pseudocode, and then you can convert the pseudocode in any language of your use. Language is secondary here. You have to write the pseudocode properly so that you can understand it clearly and everybody else also can understand it clearly. Then you will pick up a language and you will make this pseudocode to run in a computer. Then you have to make a computer code. But we have not done yet. This is only part of the algorithm. Let's move forward. Our forward elimination is now, by and large, we can say it is complete. I take pivot from 1 to n minus 1 and I keep on changing my rows up to n, and in each row aij will change, bi will change. Some of the aij's we are not changing, means that they are actually 0, so we are not talking about them. Implicitly we have taken that they are zeros. Okay, then now we start back substitution. In back substitution, we know that we have reached an upper triangular matrix if you think in terms of matrix, but even if you don't think in terms of matrix, you know that in the last equation we only have one unknown one equation, which means that it is simply xn equals bn by ann. That should be sufficient to find xn. Then in n minus 1th equation, we know that it will have xn and xn minus 1. So we can calculate xn minus 1 from there. It's very simple. And we can generalize this step for k equal to n minus 1 to 1. So we are going backward. That is why it is back substitution. xk will be bk minus summation of all the xk plus 1s multiplied by their coefficient, and all this k plus 1 we already know because we are starting from n. When we are going to n minus 1, we already know xn. Similarly, when we are going to xk, we already know k plus 1s. And of course, this is divided by akk, that is the pivot once again. This form of Gaussian elimination is the most primitive form, and it has of course serious problems especially when pivots are small. We already know that pivot 0 will certainly not work, and even when pivots are small, it will be difficult to work. So this form is the most primitive form, and let's just focus on it for now and let's sink it in. If you are familiar with Gaussian elimination, then you should be fine with this. If you are not, you go through it over and over and try to understand what we are doing in the most abstract form. This is called naive Gaussian elimination, which means is the simplest sort of Gaussian elimination. Its problem will be apparent from next lectures, but right now we'll focus only on this for some time. We now have the forward elimination and the back substitution. So if we write them together, we can have what we call is our formal pseudocode. In this pseudocode, the first part It is simply what we are doing is copying the forward elimination that we are taking. Only thing that I have done here that I put is a factor, that is aik by akk, and that factor I have multiplied both time to find aij and bi. Similarly, in back substitution, I am getting xn, and then I am summing up. There is a summation k to n. I am summing that up for aij xj here, and then this summation divided by aii. So this is essentially, I have copied the forward elimination and back substitution from what we are discussing, but here I have shown the summation in the back substitution part. When you write actual program, you can sum this way, or there are other ways. In fact, there are more efficient ways to sum this. In case the number of equations and unknowns are large, we can devise efficient ways of summing it, but it is the most primitive way, you can say. And we sum aij and xj in this way, and then we divide the entire sum by aii. That will give us the xi. Back substitution, of course, cannot be done all at a time. One by one we have to do, because to get the summation we need some other x's. We have to calculate them first. If you are familiar with this idea of Gaussian elimination, if you have written a program on Gaussian elimination, then this is something very rudimentary for you. But if you have not done so, you try writing a computer program for Gaussian elimination. Do not focus on the program itself, focus on the pseudocode. Try to understand the pseudocode. The pseudocode which I have shown here, it may not be entirely correct. You have to go through it all over again. I have written it, and everybody can make mistakes. I also make lots of mistakes when I do this, and it's very easy to make mistakes when you make something very abstract and lots of indices of I, j, k's, etc. It's very easy to make a mistake. We learn from our mistake, but nevertheless we keep on doing mistakes. So you look at this pseudocode that I am showing here, but you also write on your own, and then and only then you go for writing a program. Don't jump in your computer and write a program. Of course, many of you have done other courses on numerical method and you are quite familiar with Gaussian elimination. For them, it's not a problem at all, but those who are starting new, you spend time on writing the pseudocode, understanding the steps, and only then you go for writing a program. Once you write the program, you can try solving this set of equations. This set of equations you have solved before, probably manually without using a computer program. Now you should be able to check your results if you have done it correctly or not. That's all for this lecture. I'll see you in next class.